Okay, I think we can get started. Hello, everybody. Welcome to the ASTRO 3D ECR Astronomers in Australia seminar series. My name is Amelia Fraser McKelvey. I will be chairing today along with my co-host Anisha Harshan. Before we begin, it's important for us to acknowledge the traditional owners of the land on which we meet today. The Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing systems of knowledge on which we continue to build. We acknowledge the traditional custodians of the unceded lands on which we are meeting today. I personally am speaking to you today from the land of the Whadjuk Noongar people. My co-chair Anisha is on the land of the Bedegal people, and our speakers today are from Monash University, and they're presenting on the land of the Wurundjeri and Woiwurrung people of the Kulin Nation. We pay our respects to their elders, past and present, and extend that respect to all First Peoples joining us here today. Okay. So we are going to get started today. We've got two very exciting talks, both on the topic of gravitational waves. Our speakers are Shanika Galaudage and Isabel Ramirez-Shaw. So Shanika is going to be speaking first. So Shanika, do you want to go ahead and share your slides? You've got 20 minutes. I'll be giving you a verbal warning with 5 minutes to go. And could I ask that all guests stay muted and keep your questions for Shanika until the end? Okay, go ahead.
Thank you for the introduction, Amelia. So hi, everyone. I'm Shanika. I'm a PhD student at Monash University. I'm also a member of the LIGO collaboration and OSGRAV as well. And today I'll be talking to you about the population properties of binary black holes, and particularly the updates from the first half of the third observing run from LIGO and Virgo. So let's talk about gravitational waves. So gravitational waves, these ripples in space-time, we can detect them using current ground-based interferometers such as LIGO and Virgo. And we have so far detected gravitational waves from compact binary coalescences. So these are compact binary systems that go on to merge, such as binary black hole systems or binary neutron star systems, or a neutron star black hole system. And you can use parameter estimation programs such as Bilby to analyze these gravitational wave signals using Bayesian inference to extract the source properties of these compact binaries, such as their masses, their spins, or their inclinations, and so forth. So from these analyses, we can get these distributions for each of these parameters. And so we can do this for all of the events that we detect. So what did we have before we had O3a, or the first half of the third observing run for LIGO and Virgo? So this is what our catalogue looked like. So here we have on the right a diagram of a stellar graveyard. So these are the corpses of stars. And so these blue dots represent the black holes seen in LIGO and Virgo through gravitational waves. And the purple represents the electromagnetic black holes seen through electromagnetic observations. And the yellow dots represent neutron stars seen through electromagnetic observations. And the orange represents the binary neutron star we saw in LIGO and Virgo. So this first catalogue, we only had 11 compact binaries, 10 of which were binary black holes and 1 binary neutron star. But if we fast forward to more recent times, our second transient catalogue, which includes the first, the second, and the first half of the third observing run, we have a total of 50 compact binaries. So you'll see this stellar graveyard has suddenly exploded with a lot of these blue sources, which is fantastic. So we have 47 confident detections in this catalogue, 44 of which are binary black holes. We have 2 binary neutron stars and 1 possible neutron star black hole system. So this is what we have in our second gravitational wave transient catalogue. And so when we have so many events, rather than looking at just the individual sources parameters and trying to understand them individually, we can look at them at a population level. And to do this, we need something called population inference. So with these many events, we can start to look at these sources on a population level and extract the physics from the population. So this uses hierarchical Bayesian inference, which is a level up from Bayesian inference in the sense that Bayesian inference allows us to get the parameters such as mass and spin directly, so the probability distributions for those parameters, whereas hierarchical Bayesian inference is looking at the shape of this distribution rather than the parameter itself. So hierarchical Bayesian inference looks for parameters such as, say, the mean or the standard deviation of a distribution rather than the parameter itself. And so by looking at the population and analyzing it, we can start to probe things such as stellar evolution and the formation mechanisms of these compact binaries. And this is done through the fact that the models that we use for these inference calculations are motivated by the astrophysics. So the theory that we have, we design our models to have features that represent things in theory, and then we compare this or analyze our data and compare different models to see which one fits our population best. So in this talk, I'm going to be talking about some key results from the populations paper from LIGO and Virgo, and particularly some of the mass and spin results. So let's talk about mass. So when we look at the mass distribution and analyze it, we're looking for distinct features in the population that are motivated by the astrophysics. And in this paper, we explored multiple different mass models, and they were extensions from the models that we used in the first gravitational wave transient catalogue analysis. So things we look for are, for instance, if there is a cutoff at higher masses, or whether there is a tail at high masses, or if there are any dips or peaks within the mass distribution. And I'm going to go through a few examples of how this astrophysics can relate to the models that we use. So first up, pair instability. So when we have, so in this process, you have very massive stars with masses greater than 130 solar masses at 0 age main sequence. And these stars are so massive that they produce these positron-electron pairs. And as these are produced and released, the pressure in the core decreases and causing the core to contract. And this results in a really strong outwards pulse, resulting in the star completely blowing up. This means that there's no remnant left behind. So you don't have a black hole forming in this scenario. So what would this look like when you're looking at the mass distribution? What would be a feature that we would see? So here I have a sketch of a mass distribution, so mass against the probability, and there is a cutoff at high masses as a result of this process. So at some point, these stars are no longer collapsing down to form black holes, so we expect no more black holes to be formed beyond a certain mass. So that's what we would expect with pair instability. Another process is pulsational pair instability. So this scenario is similar to pair instability, except we have pulses. So instead of the star completely blowing up in one go, it sheds its mass over and over again until it reaches masses below around below about 80 solar masses. So this process occurs for stars between around 80 to 130 solar masses at 0 age main sequence. And so they reduce their mass down to similar mass stars and then undergo a core collapse supernova and collapse down into similar mass black holes at around 35 to 45 solar masses. So through this process, what we would expect is a pileup of black holes just before the cutoff. So if we were to look at the mass distribution, here we have the probability against mass again. Here you have this mass distribution, and then there's a peak before you have no more black holes. And so this pileup is due to the fact that you have this range of stars that have gone down to similar mass stars, and all these similar mass stars have collapsed down to similar mass black holes. So we would expect this pileup type feature when we look at the mass distribution. So these kind of features are things that we can model and look for in our analyses. So what did our results actually look like? So here are some models that we used in our population analyses. These are 4 different mass models, and these are all mass distributions. The solid line represents the mean of the distribution, and the shaded regions represent the 90% credible interval. And so I'm going to run through each of these models with you. So the first one is the truncated model. And so this is a simple power law with sharp cutoffs at the upper and lower mass end. Next, we have something called power law peak, which has a power law and a peak. And this peak is motivated by that pulsational pair instability, so that pileup of black holes. We also have a smooth turn on rather than a sharp cutoff at the lower mass end. Next up, we have broken power law. So this is essentially two power laws, and when they meet, there's like a break. And we also have the smooth turn on rather than a sharp, abrupt cutoff. And finally, we have multi-peak, which, like its name suggests, it has multiple peaks, and it has a power law with this pulsational pair instability peak, as well as this high mass peak. And this high mass peak is maybe related to what we call hierarchical mergers, which you have mergers of mergers, and Isabel will be talking more about this in her talk. And this model also has a smooth turn on at the lower mass end. So the whole point of looking at different mass models is to be able to see which one is preferred. So what we do find is truncated is not preferred. There are features beyond just a simple power law. So looking at some features a bit more closely, we can look at both the peak and the broken power law model, because those were our most favored models. And so this figure on the right represents the fraction of binary black holes in that peak for our power law peak distribution. So you have binary black holes in the power law as well as in the peak component. So this is peaking away from zero. And if you were to zoom in into this corner, it would be excluding zero. And this suggests that because it excludes zero, it means that there's no support for not having a peak, suggesting there is this peak-like structure, even though it's only around just under 10% of these binaries being in that peak part of the mass distribution. On the other hand, if you look at the broken power law model, here the axes represent the indices of our power laws. So alpha 1 and alpha 2 represent the slope of each power law, and the dashed line represents where these slopes are equal. And so you'll notice that this green region where we have support excludes this dashed line, suggesting that there is distinct slopes to these two slopes. So you do have this break-like feature in your distribution when you look at this model. So what we can conclude here is that we do have features beyond just a simple power law for our mass distribution. So this was one of the key results from the mass side of the analysis from this populations paper. So that's enough about mass. Let's talk about spin. So by looking at the spin distributions and the orientations of black holes, we can get clues as to how they formed and their evolution. So here I have a diagram of a lovely binary black hole. The white arrow represents the orbital angular momentum. The purple arrows represent the spin vectors. The theta values represent the angle of misalignment with respect to the orbital angular momentum. And these blue arrows represent the component that's in plane. And so an interesting thing is that if you have in plane components of spin, your binary will actually precess. So this is one of the things that we look for on a population level. Do we see signs of precession? What do we find? So we look for this, and we do find evidence for spin-induced precession. So let me walk you through this figure on the right. So here we have a parameter that represents the fraction of binary black holes that are preferentially aligned with the orbital angular momentum. And this parameter here represents the width of the distribution for your misalignment angle. So what this essentially means is if you look at this region in the parameter space where the fraction equals 1 and the width equals 0, this represents a perfectly aligned system or population. So if you had support here, it would suggest that your systems have support for being perfectly aligned. But what we see is that this orange distribution is well away from this perfectly aligned region of parameter space. given that this region is excluded, we can conclude that indeed we have evidence for precession on a population level. So this is one of the interesting results to come out of this paper. So another thing that we look for, or we can look for when we're doing population analyses, is to study what features represent different formation channels for binary black holes. So we can probe for the binary evolution. So there are two scenarios for binary black holes and how they evolve. We have isolated binary evolution and dynamical binary evolution. So in the first case, you have two stars that are living their lives together, and as they live with each other, they undergo tidal effects and they become more aligned with the orbital angular momentum, and eventually one of them will die, become a black hole and impart a kick, but the kicks are not so massive that they completely disrupt the system or anything like that. And then the other one will collapse into a black hole, and now you have a black hole binary. And so the key thing here is these black holes have lived their lives together and have died together, and they have preferentially aligned spins. In the second case, with dynamical binary evolution, these are black holes that have never met before, and then suddenly they capture each other and form a binary. In this scenario, there's no reason why these spins should be preferentially aligned with the orbital angular momentum, for example. So for this kind of scenario, we'd expect random spin orientations. So on a population level, what would this look like? So for isolated binary evolution, we'd expect to see spin orientations that are preferentially aligned with the orbital angular momentum, whereas for dynamical, we would expect an isotropic distribution in the spin orientations. So those are two things that we look for. So what do we see? So we do see a preference for aligned spins, and here on the figure on the right, I have this cos theta against the probability. And so this theta is the misalignment angle from that diagram. And you'll notice that this is that the values of 1 are preferred. So it's not an isotropic distribution. We have a preference for 1, suggesting that there are preferentially aligned systems in our when we consider the population. So we have a preference for aligned spins. So this is one of the results, but we also have evidence for misaligned spins. So misaligned spins being spins that are tilted more than 90 degrees with respect to the orbital angular momentum. So if we look at this figure over here, chi effective is the effective spin parameter, and values above 0 are within 90 degrees and values below 0 are tilted more than 90 degrees. And you can see support for values below 0. And in fact, looking at these results, we have 12 to 44% of the binary black hole population being tilted more than 90 degrees. And if we assume that misaligned spins are a signature of dynamical binary evolution, we can consider this as evidence for dynamical binary evolution, given that we don't expect misaligned spins in an isolated binary evolution scenario. So what does this mean? We have evidence for both scenarios. So we have a preference for aligned spins, and the distribution is not purely isotropic, but we also have evidence for misaligned spins, suggesting that there are binaries that have dynamically formed. And if we, again, assuming that spin orientations greater than 90 are from these dynamical interactions, is how we say that we have evidence for misaligned, evidence for aligned, and therefore evidence for both of these formation channels. So to summarize, we have features in the mass distribution that are beyond a simple power law with just sharp cutoffs. So we have evidence for this peak-like and break-like feature. We also have evidence for spin-induced precession. We have a preference for aligned spins and evidence for anti-aligned spins. And this supports both the isolated and dynamical formation channels, suggesting that we may have both. We don't have clear evidence for hierarchical mergers on a population level in this paper, given that the multi-peak model wasn't preferred compared to the other models. but look in the space of the LIGO papers, and there may be some papers out there related to this. And of course, this work is presented on behalf of the paper writing team for this paper, which I was a part of. And a lot of work went into this, and we're excited these results are out there. And there are my contact details, and I will take any questions now. Thank you.
Fantastic. Thank you very much, Shanika. Anisha is going to be chairing question time.
If you have any questions, please feel free to unmute yourself and ask, or just write them in the comment box, the chat.
While everyone's thinking, perhaps I can get us started. Shanika, I know very little about gravitational waves, this field of research, but I was wondering, what do we expect for the fraction of isolated binaries versus dynamical binary evolution? Is there any theoretical constraints on these values?
That's a very good question that I'm not sure about. I guess it depends on which environments are more likely. So for example, we believe with dynamical evolution, we'd expected environments such as globular clusters, whereas isolated, I guess, you would expect in calmer environments. I'm not sure what the ratio between the two would be, but yeah, I don't have a good idea about that in terms of the fraction between the two. But on what we're seeing, we're only seeing from our analysis only 12 to 44% misaligned. So if we say that's an indicator of how much of the population we expect to be dynamically formed, then we can say it's 12 to 44% of the population.
Great, thanks.
I'd also ask a question since there's no other questions from the audience. I, again, like Amelia, I'm not, I study galaxies, don't know anything about black holes in particular. But since you find evidence for both dynamical formation and like aligned spin, is there models that, or in literature that can, like a dynamical formation scenario can lead to an aligned spin?
A dynamically formed scenario that can lead to an aligned spin.
Is that possible at all?
I can't think of a scenario where that could happen unless there's, I don't know, like if you have very misaligned spins and then there's something extremely volatile that makes them align themselves, but I can't think of a scenario off the top of my head that would where that would happen. But that's an interesting question. Something that for me to think about. Do we have a question from Arthur?
I have a quick question. If I wanted to say simulate my own population using these models, how would I go about getting the data that you used to make these?
So all these results are publicly available. I should have probably included a link to that on these slides. That would have been handy. I can, if you want to send me an email, I can send you a link to it. But I'm pretty sure you could look on the LIGO website and there's a DCC link there, and I can probably send it in the chat actually during this. But they're all publicly available, and you can use for example, the mass distribution, the posterior predictive distributions to draw samples from those populations if you want. So yes, they're all available. I just need to provide the links.
Oh, that'd be great. Thank you very much.
Great. I think we can move on with the next speaker.
Okay, well, please join me in thanking Shanika again for a fantastic talk.